Another cycle to study is the ideal jet propulsion cycle. It's based on the Brayton cycle because in an ideal jet propulsion cycle, there's a compressor and a turbine, much like in a regular gas turbine engine. So you'll notice that the TS diagram for the jet propulsion cycle on the right looks a lot like the one on the left that is for a gas turbine cycle, or Brayton cycle, without regeneration. Now you'll notice that on the right-hand side, the ideal jet propulsion cycle has a couple of intermediate states during the compression process on the left, the vertical line on the left, state 1, 2, 3, and on the right during the expansion process in the turbine from state 4 to 5 to 6. Now why do we have state 1 to 2 in the gas turbine cycle being all of it, and in the ideal jet propulsion cycle we've got 3 states being all of the isentropic compression process? Why indeed? Well, the reason is because the jet engine works a little bit differently than the simple gas turbine. The key difference is the addition of a diffuser on the front of the engine and a nozzle on the back end. Now, if you look at these and consider the cross-sectional areas, the diffuser looks more like a nozzle and the nozzle looks more like a diffuser. But the idea is that the entrance to the diffuser is smaller than the exit of the diffuser. So moving from state 1 to state 2 is moving through the diffuser, so the area at state 2 is greater than the area at state 1, even though this graphic doesn't really illustrate it properly. So what happens in this engine is very much like what happens in the gas turbine engine, except that there's the diffuser at the beginning. So state 1 to state 2 is an isentropic compression in a diffuser, at least ideally. You understand this is the ideal jet propulsion cycle. No diffuser is going to be isentropic. But again, hopefully we can get close by designing it well. From state 2 to state 3 is compression in a compressor. And so that is, again, ideally isentropic compression. And state 3 to state 4 is very much like what would happen in a regular gas turbine engine, where fuel is added to very hot air so that it burns in a continuous fashion. And one key thing to note about gas turbine engines and jet engines and so forth is that anytime you have a compressor wheel and a turbine, you really want it to operate continuously. In a piston cylinder device, you can put in a charge and light it up and do more of a batch process of burning fuel. But in these bladed type engines where you have compressor wheels and turbine wheels, you typically have a more continuous burn. And I really am interested in this type of engine because it's much easier to tightly control a continuous process than a batch process. So anyway, moving on, from state 3 to state 4 is the burner section, and this is just an open section, so the pressure is constant from state 3 to state 4. And this is where, of course, fuel is added and burned. So this is our constant pressure heat addition process. And then going from state 4 to state 5 is the move through the turbine, where the hot gases expand in the turbine, going down to reduced pressure, giving up energy along the way. Of course, their enthalpy decreases because it's both the thermal energy and the flow energy, in other words, the enthalpy, that is given up from the fluid in order to drive the turbine blades. And then from state 6 to state 1, from state 5 to state 6 at the end of the engine in the nozzle is further expansion, isentropic expansion in the nozzle, and then from state 6 to state 1 is constant pressure heat rejection. Now, that constant pressure heat rejection would occur in the atmosphere, and of course, as usual, we'll replace that process with a heat exchanger, essentially, that takes the hot air out the back of the engine and then puts it back in the front. So anyway, this is the jet engine cycle, and there's a couple of important things to note. First of all, if you look at the cycle diagram, you'd realize that really state 1 all the way to state 3 are related isentropically. And so for the very simple ideal jet propulsion cycle, all you really need is an isentropic relationship between states 1, 2, and 3. And depending on the problem, you just use whichever states are convenient. From state 3 to state 4 is constant pressure heat rejection, then 4 to 6 is isentropic expansion, another move through 3 states that are all isentropically related, and then 6 to 1 is constant pressure heat rejection. Now, there's of course an energy balance that we can consider in all of these sections of the jet engine, and that energy balance has to include enthalpies as well as velocities, because the purpose of a jet engine like this is not so much to generate work output. As a matter of fact, the majority of the work produced by the turbine is used to drive the compressor. Now, in a real jet engine or a real plane, yes, some work is extracted to drive things like hydraulic pumps for controlling control surfaces or moving control surfaces on the wings. Some power is extracted for generating electricity, for in-cabin electronics and lights and so forth. Some energy is extracted. I'm not sure if it's off the engine itself, but some energy is certainly extracted and used to drive air conditioning and things of that nature. So there's more to it than what you see here, but for all practical purposes, there's a relationship between the output work of the turbine and the input work to the compressor. And we'll get to that in just a second. For right now, just understand that you can write an isentropic equation. You can use a state 1, 2, 3, interchange them however you want. They're all isentropically related in the ideal jet propulsion cycle. During the heat addition process in the burner, the best equation there is an energy balance that notes that any thermal energy that comes in via heat increases the enthalpy of the air flowing through that section. And of course, an isentropic relationship is appropriate for the last three states, going from the inlet of the turbine all the way through to the exit of the nozzle. And then an energy balance for the heat loss in the atmosphere is an appropriate equation as well. Now, all of that's well and good, and you should use them, but there's a couple of other equations you really need that are unique to the jet propulsion cycle. One of them is the energy balance around the diffuser itself. So while there is an isentropic relationship between states 1 and 2 across the diffuser, the energy balance here will also come in pretty handy. And so the enthalpy change between the two states of the air is just driven by the kinetic energy. In other words, there's excess kinetic energy coming into the diffuser, but since the flow area increases and the flow slows down, that energy can't be destroyed, and so what happens is that kinetic energy is changed into enthalpy, flow energy and thermal energy, in other words. And so that equation is very useful. Often we will neglect the exiting velocity of the air coming out of the diffuser and going into the compressor, and so a lot of times this energy balance will have the kinetic energy term, the velocity at the exit of the diffuser, just crossed off. Similarly, an energy balance is particularly useful for the nozzle at the back end of the engine. And what it does, of course, is actually a very important function. The outlet gases at state 5 still have a significant amount of energy in them. As a matter of fact, that energy is so great, some of it can be converted and used to generate kinetic energy, because really the purpose of a jet engine is to generate kinetic energy. It's to push air, essentially, out the back of the engine so hard and so fast that the engine is pushed forward, and therefore the craft that the engine is attached to is also pushed forward. Now again, with this nozzle, a lot of times we will assume that the kinetic energy of the air when it exits the turbine is so low that it's not worth including in the equation, and that the kinetic energy at the exit is completely generated from the change in enthalpy. Now, there's one more equation that is very important, and it is related to an energy balance as well between the turbine and the compressor. As I said before, most of the time we will assume, at least always in the ideal jet propulsion cycle, we will assume that the work produced by the turbine is consumed completely by the compressor. So you might look at this and say, well, that doesn't seem right, because so far all of these engines that we've dealt with have produced significant shaft work. And if this turbine blade is turning really fast, which is the case for these engines, it seems like there could be a lot of work available there. Well, it is, but it's all consumed, essentially all of it is consumed by the compressor. Because remember, we're dealing with a gas, and when we start talking about vapor power cycles, where the working fluid can move back and forth between the vapor and liquid phases, you'll see that the amount of energy required, or the power that's required to recompress the liquid, is a very small fraction of the power generated when the liquid that's been boiled off goes into the vapor phase or in the gas phase and then expands through the turbine. We don't have that luxury here. We're compressing a gas that has a relatively high specific volume, and so that takes a lot of work. And along the way, it doesn't take all of the energy that we put into the air. The air leaving state 5 still has a significant amount of energy. So The main place where thrust is developed is in the nozzle of this engine, not by, driving a propeller with these blades to pull the craft through the air. Now there are turboprop, I think they're called turboprop planes, turbofan. No, turbofan I think is the right term. We usually don't study those. They are in your book. If you want to read them, you're welcome to. But turbofan engines do include something that, it's not exactly a propeller. Basically, a turbofan engine includes a fan on the front that pulls extra air through. So some of the work produced by the turbine is used to drive the compressor. Some of the other work produced by the turbine is used to drive the fan, and then the fan helps to pull air through and accelerate the air, pulling the craft through the air. Those are actually more efficient and more common than a strictly speaking jet engine. But anyway, here's what you need to know for the ideal jet cycle. If the work produced by the turbine is equal to the work consumed by the compressor, what that means then is, since the mass flow rate through the compressor and the turbine are essentially equal, neglecting the fuel and the combustion products, since those two flows are essentially equal, then the enthalpy change across the compressor is equal to the enthalpy change across the turbine. That's a very important equation to know. It's based on the idea that all of the work produced by the turbine is consumed by the compressor. And so if we approximate these changes in enthalpy as Cp delta T, the heat capacity at constant pressure would cancel out. And here's a relationship. You should probably tab your book where this cycle diagram is located, and you should probably write this equation and the others that I've already gone through on this slide next to the cycle diagram. If they're already in the book, you might just highlight them, but I would recommend definitely tabbing this page and having these equations nearby. So the next thing we usually do is take 1 minus Qin over Q out and calculate the efficiency and so on, but that doesn't work very well here, because really the goal of a jet engine is to produce thrust, right? And so really what a jet engine does is it changes the momentum of the air before the engine to the momentum of the air after. In other words, it increases the momentum of the air significantly by a great amount. And if you remember from dynamics, the way we calculate for fluids, we calculate thrust and things, is F equals the rate of change of momentum of that fluid. And so if you know the mass flow rate of the fluid through the engine, and you know the velocity at the exit of the engine and the velocity at the entrance of the engine of the air, you can calculate the thrust. Now the propulsive power is what we use to quantify the output of the engine, and so the propulsive power is equal to the thrust multiplied by the velocity of the aircraft. And this should make sense to you. If an aircraft is sitting on the runway and its brakes are on and it's not allowed to move, and yet they throttle up the engines, that's 100% loss, isn't it? There's no flying through the air. There's no velocity of the craft, which is the goal. And so the propulsive power in that case is zero, right? There's no propulsive power. So the thrust times the velocity of the craft is, if you look at the units, it's a unit of power, and it's called the propulsive power. To calculate the propulsive power, we use the thrust multiplied by the velocity of the aircraft, and of course the thrust substituting in the equation at the top of the slides. The thrust is the mass flow rate times the velocity change across the engine. Now you have to be careful with this equation. The velocity of the air coming into the engine and the velocity of the air leaving the engine have to be taken with respect to the same reference frame. You can't take one with respect to ground and the other one with respect to the aircraft as the craft moves through the air. That won't work. So be careful about that. So here it doesn't matter whether you take the airplane as the reference frame or the ground and measure the velocity of the air flowing into the engine and out. As long as you've used a consistent basis, this difference will be fine. The other one, though, the velocity of the aircraft has to be taken with respect to ground. Obviously, if you're standing on the craft, the velocity of the craft relative to your frame, which is on the craft, is zero. So that doesn't work. The velocity of the craft has to always be taken with respect to ground. Then finally, we can calculate the so-called propulsive efficiency as the propulsive power divided by the energy input rate of the fuel, Q dot N.